In 1980, a father and son, Luis and Walter Alvarez, split open a thin layer of clay near Gubbio, Italy, and found iridium where it should not have been. A metal rare on Earth's surface, but common in asteroids, pressed into a band no thicker than a fingertip yet, stretching across every continent they tested. That single layer told the story of the end of the dinosaurs. It had been sitting in the rock for 66 million years waiting for someone to read it. If one event could leave so quiet a fingerprint for so long, what else might the deeper, older pages of stone be holding that we have never thought to look for? Tonight, we sit with a version of that question turned not toward the sky, but downward into the ground beneath us. What if another civilization came before us millions of years before the first human ever stood upright and left almost nothing behind? This is not a claim. It is not even a theory. It is a thought experiment, one that serious scientists have explored, and the answers they found are more unsettling than silence. Over the next while, we will follow three quiet threads: the chemical fingerprints that industry presses into rock, the deep ocean sediments, where the Earth keeps its longest memories, and the restless geology that erases nearly everything this planet has ever known. To understand why this question lingers, you have to start with time. Not the kind measured in years or centuries, but the deep time that belongs to the Earth alone. Our planet is 4.5 billion years old. If you compressed all of that into a single day recorded human history, every empire, every cathedral, every language we have ever spoken would appear in the final fraction of a second before midnight. Everything else would pass in silence. And silence is exactly what deep time leaves behind, and the surface of the Earth is not a stable archive. It is a restless canvas rewritten again and again by forces we can barely perceive. Tectonic plates drift across the planet like slow rafts on a hidden sea of molten rock. They collide, pull apart, and slide past one another. Mountains rise where they meet. Oceans open where they separate. And in that long process, the ground itself is recycled, melted, remade, and laid down as something new. This is why almost no surface rock is truly ancient. The ground beneath your feet is young compared to the planet it covers. Most of the original crust has been dragged into the mantle and destroyed. Entire continents have come and gone. Mountain ranges, once tall enough to rival the Himalayas, have been worn to low hills and buried roots of stone. If you built a city today and left it untouched, 1,000,000 years would be more than enough to erase it completely. Not just the buildings, not just the roads. The very land it stood on might be gone, subducted beneath an ocean trench, or buried under kilometers of sediment that no one will ever dig through. And here is where a quiet number changes everything. The ocean floor, the single largest surface on Earth, is less than 200 million years old. Not because nothing existed there before, but because the planet recycles it. Old crust is pulled down at the trenches, melted and remade into fresh rock. Anything that once rested on an older seabed is gone. On land, the record survives, only a little better. Rocks billions of years old do exist in a few rare places, parts of these Greenland, Western Australia, northern Canada, but they have been so altered by heat and pressure that they can barely hold the fine details of what once happened near them. So when scientists ask whether another civilization could have existed before ours, they are not asking a fanciful question. They are testing the limits of what the Earth itself can remember. In 2018, climate scientist Gavin Schmidt of NASA and astrophysicist Adam Frank gave this thought experiment a name: the Silurian Hypothesis, a playful nod to a fictional species of intelligent reptiles from an old television story. But behind the light title was a serious inquiry. If an industrial civilization had risen on this planet tens of millions of years ago, what traces would survive? And could we tell them apart from the ordinary noise of geology? Their answer was both reassuring and disquieting. Reassuring because our own civilization is already pressing signals into the rock that will persist for millions of years. We burn fossil fuels, and in doing so we shift the balance of carbon isotopes in the atmosphere. Those shifts will be recorded in stone. We mine copper, aluminum, and lead, spreading them in concentrations that no volcano or ocean current could produce. We manufacture plastics and synthetic compounds that will break down over time, but may leave microscopic fragments locked in a deep ocean sediment, sealed away like strange stubborn little time capsules. If we vanished tomorrow, the Earth would grind our cities to dust within a few 100,000 years, but those chemical fingerprints would remain, A thin, peculiar layer in the rock, no different in principle from the iridium band that marks the death of the dinosaurs. And that is what makes the question so difficult to set aside. Because if we can leave such a mark in just 2 centuries of industry, then the thought follows naturally, could someone or something else have done the same long before us? Not necessarily with towering cities or gleaming machines, but as a brief pulse of chemical disruption pressed into the rock and then buried under millions of years of new stone, resting in the dark for anyone patient enough to look. So far, nothing like that has been found. That deserves to be said plainly. There is no confirmatory trace of a pre-human industrial civilization anywhere in the geological record. But what the Silurian Hypothesis reveals is something more subtle, that our tools for reading the deep past may not yet be fine enough to rule the possibility out entirely. Most of the ocean floor remains unmapped in detail. Most deep rock layers sit far beyond our reach. We are creatures perched on the newest, thinnest layer of world that has been rewriting itself for longer than we can hold in our minds. And so the question stays open, not as belief but as honest uncertainty. A reminder that on a planet this old, the absence of evidence may say more about the limits of our search than about what the Earth has witnessed. Tonight we follow that uncertainty downward through the chemistry of ancient stone, through the silent sediments beneath the ocean, through the slow, patient machinery of a world that forgets almost everything, and yet sometimes holds on to just enough. Let us begin where the traces are faintest of the weight of 4 billion years. In the Jack Hills of Western Australia. Inside a piece of rock no larger than a fist, geologists have found crystals of zircon that formed 4.4 billion years ago. They are among the oldest surviving materials on Earth's surface. Tiny translucent grains, barely visible to the naked eye, each one a sealed capsule of the planet's infancy. To hold one under a microscope is to look at something that existed before the oceans had settled, before the continents had taken shape, before the first flicker of life had begun anywhere on this world. And yet these crystals survived. They endured the grinding of tectonic plates, the pressure of burial, the slow heat of deep stone. They were carried upward by geological accident and deposited in a stretch of dry, ancient terrain, where they waited for billions of years until someone thought to look. That fact alone is worth sitting with, because if something so small and fragile can persist across nearly the entire history of the Earth, it tells us 2 things at once. First, that the planet does not erase everything, and second, that what it chooses to keep is not what we might expect. We tend to imagine the past as something preserved in recognizable forms. Bones in museum drawers, ruins half buried in sand, pottery shards and carved stone and the outlines of walls that once held roofs. That is how human history survives in objects we can name and understand. But the deeper you go, the less the past looks like anything we know. At the scale of millions of years, the Earth does not preserve stories. It preserves chemistry. It preserves pressure. It preserves faint molecular arrangements locked inside minerals that most people would walk past without a second glance. This is the world the Silurian Hypothesis asks us to consider. Not the surface world of monuments and meaning, but the underground world of isotopic ratios, trace metal concentrations and sedimentary layers where the only surviving record of an entire era might be a slight change in the colour of clay. The hypothesis itself, proposed in 2018 by Gavin Schmidt and Adam Frank, does not claim that a pre-human civilization existed. It asks a narrower, more careful question: if one had existed, say 50 or 100 million years ago, what kind of evidence could we realistically expect to find today? The answer depends almost entirely on what the Earth does to things over time. And what the Earth does, with rare exceptions, is destroy them. Consider what happens to a modern city if it is simply left alone. Within a decade, vegetation begins to crack the pavement. Within a century, most structures have collapsed. Steel corrodes, glass shatters. Concrete, which we think of as nearly permanent, begins to eat and crumble as water seeps through its pores. Within 1,000 years, almost nothing above ground would remain recognizable. The footprint might still be there, a faint rectangular depression in the soil, a slight chemical difference in the ground, but the city itself would be gone. Now stretch that timeline. 10,000 years, 100,000, 1,000,000. At each step, the traces become fainter. The rectangular depression fills with sediment. The chemical difference diffuses. Rivers shift their courses and wash through what was once a downtown intersection. Forests grow, die, and grow again, their roots churning the soil until even the faintest outline is mixed into the general texture of the land. And 1 million years in geological terms is almost nothing. The Earth is 4.5 billion years old. 1 million years is to that span what a single second is to roughly a day and a half. If you are looking for something that happened 50 million years ago, around the time the first modern mammals were beginning to diversify, you are not looking through a slightly dusty window. You are looking through a window that has been buried under kilometres of stone, shattered by earthquakes, compressed by the weight of mountains, and in many places melted entirely and reformed into something new. This is where the Jack Hill zircons become more than a curiosity. They survived because they are extraordinarily hard, chemically stable, and small enough to ride the slow currents of geological recycling without being destroyed. They are in a sense the ultimate minimalists, carrying almost no information about the world they came from, but carrying proof that the world existed. If an entire civilization's legacy could be compressed into something that durable and that small, it might still be here, but it would not look like a civilization. It would look like a grain of sand with an unusual atomic signature. And that is the quiet paradox at the centre of this question. The Earth has had more than enough time for complex life to rise, flourish, and disappear not once, but potentially many times. 4 billion years of biological experimentation of shifting climates and reshuffled continents of countless species emerging and vanishing without leaving a single fossil. We know this because the fossil record itself is riddled with gaps. For every species preserved in stone, paleontologists estimate that thousands more lived and died without any trace at all. The record we have is not a complete history. It is a scattered handful of pages, torn from an enormous book, most of which has been lost. If entire species can vanish without a trace, then the disappearance of a civilization, something far more recent and far more fragile than a biological lineage, is not just possible. It is given enough time, almost inevitable. And so we begin not with evidence, but with the absence of it. Not with proof that something was here before us, but with the recognition that the Earth is extraordinarily good at making things disappear. The question is not whether this planet could hide a lost chapter of its history. The question is whether it could do anything else. That thought leads us inevitably to the machinery responsible for hiding the restless engine of plate tectonics and the slow, relentless recycling of the ground beneath our feet. The engine that erases. Every year, the Atlantic Ocean grows wider by roughly 2.5 centimetres, about the speed at which a human fingernail grows. It is such a small movement that no instrument on a ship could detect it in real time, and no person standing on either shore would ever feel it happening. Yet over the course of 100 million years, that gentle drift is enough to tear a supercontinent apart open, an ocean basin thousands of kilometres wide, and rearrange the entire geography of the planet. This is the pace at which the Earth remakes itself. Not in sudden catastrophes, though those happen too, but in a slow, ceaseless motion so quiet that it took humanity thousands of years of civilization before anyone even suspected it was there. Plate tectonics is the engine behind almost everything the Earth does to its own surface. The planet's outer shell is broken into enormous slabs of rock, some carrying continents, others forming the floors of oceans, and these slabs float on a layer of hot, slowly churning mantle beneath them. Where they pull apart, molten rock rises from below to fill the gap, creating new crust along mid-ocean ridges that wind across the seafloor like stitching on a baseball. Where they collide, one plate is forced beneath the other, in a process called subduction, dragged downward into the mantle where heat and pressure will eventually melt it back into the raw material from which it came. It is a cycle of creation and destruction that has been running without interruption for billions of years, and it is the single most important reason that the Earth's deep past is so difficult to read. Consider what subduction means for anything resting on the ocean floor. The oldest oceanic crust on the planet today is roughly 200 million years old. A figure that sounds enormous until you remember that the Earth itself is more than 20 times older. Everything that once lay on an older seafloor has been pulled into the interior and recycled. Every layer of sediment, every chemical trace, every record of what the world above once looked like, all of it dragged into darkness and melted beyond recognition. If a civilization had existed 300 million years ago and left its mark on the ocean floor, that mark would now be magma. There is no technology we possess, and perhaps none we could ever build, that would recover information from molten rock deep inside the planet. The record is not merely buried, it is unmade. On land, the situation is only slightly more forgiving. Continental crust is lighter than oceanic crust, which is why continents float higher and are not so easily subducted. But they are not immune to destruction. Mountains rise where plates collide. The Himalayas are still growing today as India pushes northward into Asia, and then erosion begins its patient work. Rain dissolves minerals. Frost cracks stone apart. Rivers carry fragments downhill grain by grain, depositing them as sediment in valleys, deltas, and ocean basins. A mountain range that once stood as tall as the Alps can be worn down to a low plain in 50 million years, its substance scattered across half a continent. And whatever was on that mountain, whatever might have rested on its slopes or in the valleys at its feet, would be scattered with it, broken into pieces too small and too dispersed to ever reassemble. There is something almost unsettling about the thoroughness of this process. We are accustomed to thinking of rock as permanent as the very symbol of endurance and stability. But at the timescales that matter for this question, rock is fluid. It flows, it bends, it breaks, and it is born again in forms that carry almost no memory of what came before. The Appalachian Mountains in eastern North America were once as tall and as jagged as the Himalayas are now. Today they are gentle rounded ridges, old beyond easy comprehension, worn smooth by 400 million years of rain and ice. If a city had once stood in those ancient highlands, its atoms would now be part of the sedimentary plains of the American Midwest, or the muddy floor of the Gulf of Mexico, or the calcium carbonate shells of creatures that lived and died in seas that no longer exist. The city would not be hidden. It would be everywhere and nowhere at once. Its substance returned to the earth so completely that no instrument could distinguish it from the natural background. This is the machinery that any hypothetical pre-human civilization would have had to survive. Not a single catastrophe, not a single flood or earthquake, but the entire grinding apparatus of a living planet operating continuously across tens or hundreds of millions of years. Plate tectonics does not merely bury the past beneath new layers. It recycles the layers themselves, feeding old crust back into the furnace and producing new crust that carries no trace of what was there before. It is in the most literal sense a system designed to forget. And yet, as with so many things about this planet, the erasure is not quite total. There are places where fragments of the old world survive, not because the Earth chose to preserve them, but because geological accident kept them out of reach of the machinery. Ancient rocks in Greenland, more than 3 billion years old, persist because they were caught in a stable region of crust that happened to avoid the worst of the recycling. Certain deep ocean sediments sheltered in basins far from subduction zones hold unbroken records stretching back tens of millions of years. These are rare refuges, small windows into a past that has otherwise been sealed shut. But they exist. And if there is any trace of something older than us, any faint chemical whisper pressed into stone before the engine could reach it, these are the places where it might still be waiting. The question then is not whether the Earth could erase a civilization. It is whether the erasure could ever be complete enough to leave absolutely nothing behind. And to answer that, we need to look more closely at what a civilization actually leaves in the rock. Not its buildings, or its tools, but the invisible signatures that even the deepest burial cannot entirely destroy. What industry writes in stone, us and stone? What does a civilization look like when everything it built has been crushed, melted, and reformed into raw geology? The instinct is to say it looks like nothing, that without walls and roads and recognizable artifacts, there is simply no trace left to find. But that instinct comes from thinking in human terms in shapes and surfaces. The Earth does not remember shapes. It remembers chemistry. And chemistry, once pressed into the layers of rock, can be remarkably difficult to erase. When we burn fossil fuels, coal oil, natural gas, we are releasing carbon that was locked underground for hundreds of millions of years. That carbon, once part of ancient forests and ocean organisms, carries a specific isotopic signature. Carbon-12 and carbon-13 exist in nature in a fairly stable ratio, but biological material tends to favour the lighter isotope. When vast quantities of that biologically sourced carbon are suddenly released into the atmosphere, the ratio shifts. It is a subtle change measurable only with sensitive instruments, but it is written into everything the atmosphere touches the surface ocean, the shells of marine creatures, the calcium carbonate, sediments that slowly accumulate on the seafloor. 100 million years from now, if someone were to drill a core through those sediments, they would find a sharp, sudden excursion in the carbon isotope record. It would look like a spike, a brief, intense disruption in a curve that had been stable for millions of years before it. And that spike would be us. Not our cities, not our literature, not our names. Just a thin chemical scar in the rock recording the moment when something on this planet burned through an enormous quantity of stored carbon in what, geologically speaking, was the blink of an eye. This is the kind of trace that the Silurian Hypothesis asks us to consider. Not monuments, but molecules. Not ruins, but ratios. If an industrial civilization had existed 50 million years ago and burned through carbon-based fuels the way we do, the isotopic record of that event might still survive in the right sediments, particularly in deep ocean cores where the layering is slow, continuous, and relatively undisturbed. The signal would not announce itself. It would not say civilization. It would simply be an anomaly, a data point that does not match the expected background, and it would be up to the person reading the core to decide whether it was worth investigating further. The uncomfortable truth is that such anomalies do appear in the geological record from time to time, and in nearly every case they are attributed to natural causes. Volcanic outgassing, shifts in ocean circulation, changes in biological productivity. These explanations are almost certainly correct, but the Silurian Hypothesis points out that if the cause was something else entirely, something industrial, the signal might look almost identical. Distinguishing between a volcanic carbon release and a technological one separated by tens of millions of years of additional geological processing would be extraordinarily difficult. Carbon is not the only signature that industry leaves behind. Consider the metals we extract and redistribute across the planet's surface. Copper, for instance, does not occur naturally in thin, widespread layers. It forms in concentrated deposits created by specific geological processes over long stretches of time. But human mining has taken that copper and spread it everywhere through wiring, through plumbing, through the circuits of every electronic device on Earth. If our civilization were to vanish, that copper would oxidize, erode, and disperse, but it would not disappear. Over millions of years it would settle into sediments as a faint but measurable enrichment, a background level of copper slightly higher than what geology alone would predict. The same is true for lead, for aluminum, for the rare earth elements that power our modern technology. Each one would leave its own quiet fingerprint, a concentration that is just barely wrong, just enough to make a careful analyst pause. And then there are the truly synthetic materials, the compounds that nature has never produced on its own. Plastics, for example, are already breaking down into microparticles that are settling into ocean sediments around the world. Most of them will degrade beyond recognition within a few million years. But some fraction buried deep enough and sealed in the right conditions may persist as microscopic inclusions in the rock, tiny foreign bodies with a chemical composition that no natural process could explain. They would not look like plastic. They would look like nothing in particular. But under the right kind of analysis, their molecular structure would betray them as something that required intention to create. A future geologist encountering such inclusions in a layer of rock 50 million years old would face a genuine puzzle. Nature does not make polyethylene. Nature does not produce the particular arrangement of long-chain polymers that we engineer in factories. If those molecules, however degraded, were found in ancient stone, they would demand an explanation that geology alone could not easily provide. This is the vocabulary of deep time. Not words, not images, not anything a human eye could recognize at a glance. Just numbers, ratios, concentrations, faint molecular ghosts that linger in the rock long after every visible trace of their origin has been ground to dust. It is a vocabulary we are only beginning to learn to read, and most of its pages remain closed to us. But the letters are there pressed into the stone, and if anything came before us and burned mind and manufactured its way through, even a brief industrial age, those letters may still be legible if we know where to look and what questions to ask. The most promising place to ask those questions lies beneath the heaviest silence on Earth, the deep ocean floor. The archive beneath the waves. In 1968, the research vessel Glomar Challenger lowered a drill string through more than 3,000 meters of open water in the Gulf of Mexico and pulled up the first deep-sea sediment core ever recovered for scientific study. What came back was a cylinder of mud roughly 6 centimeters across, grey-dense and unremarkable to look at. But when geologists sliced it open and began to read its layers under magnification, they found a continuous record of the Earth's climate stretching back tens of millions of years, compressed into bands of colour and texture so fine that a single centimetre of core could represent thousands of years of planetary history. It was at that moment the longest unbroken diary anyone had ever pulled from the Earth. And it came not from a mountaintop or a famous excavation site, but from the bottom of the sea where nothing had disturbed it since the day each grain of sediment drifted down and came to rest. The deep ocean floor is the closest thing the Earth has to a permanent archive. On land, erosion is constant and unforgiving. Rivers carve glaciers, scrape winds, scours and roots break apart even the hardest stone. But in the abyssal plains of the deep sea, none of that applies. There is no weather. There is no wind. There is no sunlight, no temperature change worth measuring, no biological activity vigorous enough to churn the layers once they have settled. What falls to the bottom stays there, pressed slowly into place by the weight of everything that falls after. It's sealed in cold and darkness and utter stillness. Year after year, century after century, a fine rain of particles drifts down from the surface dust blown off distant continents, volcanic ash carried on high-altitude winds, the calcium carbonate shells of tiny planktonic organisms that lived and died in the sunlit waters above. Each particle carries with it a chemical snapshot of the world at the moment it was formed, and each one is added to the growing record with a patience that no human institution could ever match. This is why ocean drilling programs have become one of the most powerful tools in Earth science. Since the days of the Glomar Challenger, successor programs, the Ocean Drilling Program, and later the International Ocean Discovery Program, have pulled cores from every major ocean basin on the planet. Some of those cores reach back more than 100 million years into the Cretaceous period, when dinosaurs still walked the land, and the Atlantic Ocean was barely half its current width. In their layers, scientists have found the iridium anomaly that marks the asteroid impact 66 million years ago. They also traced the chemical signature of ancient volcanic eruptions, the advance and retreat of ice sheets, and the slow shifts in ocean circulation that drove entire ecosystems to collapse and reform. The record is not perfect. There are gaps, disturbances, and intervals where the sediment was lost to underwater landslides or eaten away by the corrosive bottom currents. But compared to anything available on land, it is extraordinarily complete. And it is in this record more than any other that the Silurian Hypothesis suggests we should look. If an industrial civilization existed tens of millions of years ago, its chemical fingerprints, the carbon isotope excursion, the trace metal enrichments, the faint residues of synthetic compounds would have settled into the ocean sediments along with everything else. They would be there now, compressed into a thin band somewhere in the middle of a core sandwiched between the ordinary layers of geological time. The band might be only a few millimeters thick, representing a few centuries of industrial activity squeezed into the immense time scale of the surrounding record. A drilling team could pass through it without noticing, especially if they were not looking for that particular kind of signal. And this is where the scale of the problem becomes quietly overwhelming. The ocean covers more than 70% of the Earth's surface. The total area of the abyssal plains alone, the flat featureless expanses of deep sea floor, exceeds the combined area of every continent. Yet the number of deep sea cores that have been drilled across all programs and all decades of ocean science amounts to a few thousand individual sites. Each core samples an area roughly the size of a dinner plate. The ratio of what we have examined to what remains untouched is so small that it barely registers as a fraction. We have in effect read a few sentences from a book millions of pages long, and most of those sentences were chosen not because they might contain evidence of a pre-human civilization, but because they were relevant to questions about climate, ocean chemistry, or plate tectonics. No one has ever drilled a deep sea core specifically to search for the kind of signal the Silurian Hypothesis describes. The tools exist, the methodology exists, the question has been formally posed in a peer-reviewed journal. But the search itself has not been conducted for the simple reason that it would require examining an enormous volume of sediment, with a very specific set of analytical techniques looking for something that may not be there at all. It is the kind of project that science, with its limited funding and its preference for testable predictions, does not easily undertake. And yet the archive is there, waiting beneath 3 or 4 kilometres of cold, dark water, holding within it a record of nearly everything the Earth has done since the age of the dinosaurs. If there is a signal to be found, a thin chemical whisper from a world that came and went before any human hand ever touched the soil, this is where it would be hiding. Not shouting from an exposed cliff face or a riverbed, but sealed in the quietest, most undisturbed place on the planet, where the only sound is the faint continuous rain of particles drifting down through the darkness to take their place in the record. Whether that record contains only the expected, the ordinary narrative of volcanism, climate and biological evolution, or whether it holds something stranger, something that does not fit the usual explanations, is a question we have not yet seriously tried to answer. And perhaps that is the most honest thing that can be said about the deep ocean and the Silurian Hypothesis. The archive exists, the tools to read it exist, but we have barely opened the cover, and most of the pages remain unread. Some of those pages, however, are not underwater at all. They are on land, hidden in the driest and most silent places on the surface, places where the Earth, for reasons of its own, chose not to recycle what was given to it. The vaults of sand and silence. Most geologists would tell you that a desert is one of the worst places to look for ancient evidence. The reasoning is sound, wind abrades, exposed surfaces, sand scours anything left in the open, and the relentless cycle of heating and cooling fractures even the hardest stone over time. A desert, by this logic, is an engine of destruction grinding down whatever the rest of the planet has not already buried. And for anything sitting on the surface, that assessment is entirely correct. But the surface is not the whole story, and deserts have a second quality that is far less often discussed. They are under the right conditions among the most effective preservation environments on Earth. What the wind takes from the top, the sand seals underneath. And what the sand seals, it holds with extraordinary patience. The Sahara stretches across more than 9 million square kilometres of North Africa, an area roughly the size of the United States. To stand at its edge and look inward is to see a landscape that appears timeless, as if the dunes have always been there, as if the silence has always been this deep. But the Sahara is not timeless. It is in fact remarkably young. As recently as 10,000 years ago, a span so brief that it barely registers in geological terms, much of what is now open desert was green. Lake beds filled with water. Rivers cut across the landscape. Hippopotamuses waded in marshes that no longer exist. We noted this is not from speculation, but from physical evidence. Ancient shorelines etched into rock pollen, preserved in dried sediments, and most strikingly, rock paintings left by the people who lived there. Images of elephants, giraffes, and cattle grazing on plains that are now buried under meters of sand. The transition from green to desert happened in stages, driven by a slow shift in the Earth's orbital parameters that altered the pattern of monsoon rains across the region. And when the rains withdrew, the sand came not in a single catastrophic event, but gradually layer upon layer, covering everything that had been left behind. This is what makes deserts so peculiar in the context of deep time. On the surface they erase. Below the surface they entomb. The dry air prevents the chemical reactions that break down organic material in wetter climates. The absence of moisture slows oxidation to a crawl. There are no roots pushing downward, no burrowing animals churning the soil, no freeze-thaw cycles cracking open buried objects. In the driest parts of the Sahara and in comparable deserts like the Atacama in Chile, where some weather stations have never recorded a single drop of rain conditions below the surface, approach something close to geological stasis. Objects buried there can remain almost unchanged for thousands of years, and under deeper burial potentially much longer. Archaeologists have already benefited from this effect. In Egypt and across the broader Saharan fringe, the dry conditions have preserved papyrus scrolls, textiles, wooden tools, and even human remains in states of detail that would be impossible in a temperate forest or a tropical river valley. The famous Dead Sea Scrolls survived for 2,000 years in the arid caves of the Judean desert, their ink still legible, their parchment still intact. These are human scale timescales, centuries and millennia, but they demonstrate the principle. Aridity is a form of protection. What the desert buries it does not easily surrender. Now extend that principle downward and backward. Beneath the surface dunes of the Sahara lie rock formations that are hundreds of millions of years old, Paleozoic sandstones, Precambrian basement. Rocks, layers of limestone deposited in seas that vanished long before any mammal walked the earth. These formations are not often studied in the context of the Silurian hypothesis because they are difficult to access, and because no one has had a specific reason to examine them for the kind of subtle chemical anomalies that a pre-human civilization might have left behind. But they are there sealed under a blanket of sand that in some places is hundreds of meters thick, shielded from the erosive forces that have stripped equivalent rock layers bare in other parts of the world. If there is a place on land where a faint geochemical signal from a deep-time civilization might have survived the ordinary processes of destruction, a thick desert basin, stable, dry, and largely undisturbed, would be among the better candidates. The Sahara is not the only such vault. The deserts of Central Australia sit atop some of the oldest and most geologically stable crust on the planet rocks that have remained near the surface for billions of years without being significantly deformed or recycled. The Namib Desert in southwestern Africa, often cited as the oldest desert on Earth, has been arid for at least 55 million years, a span that reaches back past the extinction of the dinosaurs and into an era when the planet looked fundamentally different from what we know today. Beneath its sands are geological formations that have been accumulating quietly for tens of millions of years, layer upon layer, in conditions that favour preservation over destruction. These are not places where anyone has gone looking for traces of a lost civilization. They are places where the Earth has simply been left alone for a very long time, and that perhaps is the most important point. We have not looked. The analytical tools exist: ground-penetrating radar, deep-core sampling, high-resolution geochemical analysis, but they have been directed at other questions. The deserts remain largely unexamined at the depths, and with the methods that the Silurian hypothesis would require. Their silence is not confirmation that nothing is there. It is confirmation only that no one has listened carefully and more ifs in the right places for the right kind of sound. Whether there is anything to hear is a separate question, and one that demands a different kind of honesty, the kind that is willing to consider what happens when the evidence is genuinely ambiguous, when the data does not clearly point in any direction, and when the most responsible answer might simply be that we do not know. That honesty is the subject of what comes next. The honest weight of doubt. It would be irresponsible to travel this far into the question without stopping to ask whether we have been too generous with possibility. The Silurian hypothesis is elegant. It is carefully framed. It asks a question that is genuinely difficult to dismiss. But elegance is not evidence, and a question that cannot be easily answered is not the same as a question whose answer is likely to be yes. If we are honest, and this kind of inquiry demands honesty above all else, we must sit for a while with the reasons to think that the answer is almost certainly no. The first and most important reason is simple: no one has found anything. Not a single confirmed trace of a pre-human industrial civilization exists anywhere in the geological record. No anomalous metal layer has been identified that requires a technological explanation. No isotopic excursion in any ocean core has been attributed to anything other than natural causes. No synthetic compound, however degraded, has been recovered from ancient rock. The hypothesis has been in the scientific literature since 2018, and in that time it has generated discussion thought experiments and a handful of follow-up papers, but not a single piece of positive evidence. That fact does not prove that nothing existed before us, but it does establish the baseline from which any further discussion must proceed. We are not debating the interpretation of ambiguous data. We are debating a pure absence, and absence, however uncomfortable it may be to say so, is what the record currently shows. The second reason cuts deeper into the logic of the hypothesis itself. One of its most persuasive features is the argument that the Earth erases so thoroughly that evidence of a past civilization might simply be undetectable. This is true as far as it goes. The planet does recycle its crust, and the geological record is full of gaps. But there is a philosophical difficulty with any argument that relies on the undetectability of its subject. If the evidence would be too faint to find, then the hypothesis cannot be tested. And if it cannot be tested, it occupies a strange and uneasy space in science, Not wrong exactly, but not meaningfully right either. It becomes what philosophers of science call unfalsifiable, a proposition that no observation could ever confirm or deny. The Silurian Hypothesis is aware of this problem. Schmidt and Frank acknowledged it in their original paper, and they were careful to frame their work as a methodological exercise rather than a claim about what actually happened. But in the broader conversation in documentaries, articles, and late-night discussions, that careful framing often gets lost, and the hypothesis begins to function less as a scientific question and more as a feeling, a sense that the world is old enough for anything to have happened, which is true, but is not the same as saying that anything did. The third reason comes from biology itself, and it is perhaps the most quietly persuasive of all. Dinosaurs dominated this planet for more than 160 million years. That is an almost incomprehensible span of time, roughly 800 times longer than the entire existence of the genus Homo. During those 160 million years, dinosaurs diversified into thousands of species. They occupied every continent. They filled ecological niches ranging from ocean-going predators to tiny feathered insectivores no larger than a sparrow. They had every advantage that deep time could offer: a stable climate for long stretched, abundant resources, and an evolutionary head start measured in tens of millions of years. And yet in all that time, not one lineage produced anything resembling tool-use language or technological civilization. Not one left a trace that suggests organized modification of the environment beyond what any animal does simply by living in it. Some paleontologists have speculated about what might have happened if the asteroid had not struck, whether certain small, large-brained theropods might eventually have developed something like intelligence. It is an interesting thought experiment, but it remains speculation, and the fossil record offers no support for it. What the record does show is that intelligence of the kind that builds civilizations is not an inevitable outcome of evolution, even given enormous stretches of time and enormous diversity of form. It happened once with us, and it happened recently. That may be because the conditions required are extraordinarily specific, or because the path to technological intelligence involves so many contingent steps that most lineages never complete it. Either way, the prior probability of a pre-human civilization is not zero, but it is low, perhaps very low, and the absence of evidence, while not conclusive, is consistent with that assessment. These are not comfortable points to raise in the middle of a story about hidden traces and unread archives. They lack the romance of imagining a forgotten world buried beneath the sand. But they are necessary because without them the question loses its grounding. The power of the Silurian hypothesis is not that it suggests something exciting. It is that it forces us to examine how we know what we know, how we read the geological record, how we distinguish natural signals from anomalous ones, and how much of the Earth's history remains genuinely beyond our reach. If we skip the doubt, we lose that power. We turn a serious scientific exercise into a campfire story, and the question deserves better than that. And yet, and this is where honesty demands one more step, none of these objections fully closes the door. The absence of evidence is real, but the search has been limited. The unfalsifiability concern is valid, but it applies to the current state of our tools, not necessarily to future ones. The biological argument is strong, but it is an argument about probability, not impossibility. The door remains open if only by a crack, and it remains open precisely because the Earth is so effective at destroying its own records that we cannot say with certainty what those records once contained. It may be natural. It may be chance. The discomfort is that we cannot yet be entirely sure, and in science that small margin of uncertainty is sometimes where the most important questions live. What we can do is look more carefully at what the Earth has preserved and ask whether there are moments in the geological record, real documented moments where something happened that still resists a simple explanation. The fever in the record. 56 million years ago, the Earth ran a fever. It came on fast, at least by geological standards, and it was severe. Over a span that may have been as brief as 20,000 years, global temperatures rose by 5 to 8 degrees Celsius. The oceans warmed from surface to floor, Arctic waters reached temperatures that would feel subtropical today. Crocodile-like reptiles swam in seas above what is now the Canadian Arctic, and palm trees grew on coastlines that are now locked in permafrost. Then, almost as abruptly as it began, the fever broke. Temperatures fell, the oceans cooled, the world slowly returned to something closer to what it had been. Though not exactly, some things had changed permanently. Species had gone extinct, ocean chemistry had been altered, and deep in the sediment record a sharp, unmistakable spike in carbon isotopes had been laid down like a scar marking the moment when something flooded the atmosphere with an enormous pulse of carbon from a source that even now no one can fully explain. Scientists call it the Paleocene-Eocene Thermal Maximum, or PETM. It is one of the most studied events in the geological record of the last 100 million years, and it is real, documented in ocean cores from every major basin, confirmed by independent lines of evidence from isotopic chemistry to fossil distribution to sediment composition. There is no dispute about whether it happened. The dispute, quiet and ongoing, is about what caused it. The leading explanations involve natural processes, a massive release of methane from frozen deposits on the seafloor triggered perhaps by volcanic activity or a shift in ocean circulation. These explanations are plausible. They are supported by modelling and by analogy with other smaller carbon releases in the geological record. Most scientists accept some version of them as the most likely account. But the detail that lingers, the small stubborn detail that the Silurian hypothesis gently underlines, is that the carbon isotope signature of the PETM looks remarkably like what an industrial civilization would produce. The resemblance is not superficial. When we burn fossil fuels, we release carbon that is isotopically light enriched in carbon-12, relative to carbon-13, because the carbon in coal and oil was originally fixed by biological processes that preferentially incorporated the lighter isotope. That is exactly what appears in the PETM record. A sudden negative excursion in the ratio of carbon-13 to carbon-12 consistent with the rapid release of a large quantity of biologically sourced carbon. The magnitude of the excursion suggests that somewhere between 2,000 and 7,000 gigatons of carbon entered the atmosphere in a geologically brief window. For comparison, human industry has released roughly 700 gigatons since the beginning of the Industrial Revolution, and current projections suggest we could release several thousand more over the coming centuries if fossil fuel use continues. The numbers are in the same order of magnitude. The isotopic signature is in the same direction. The timescale, while longer than our industrial age so far, is within the range of what a civilization might produce over a sustained period of activity. This does not mean the PETM was caused by a civilization. It is important to say that clearly, because the evidence does not point in that direction. There are no accompanying metal enrichments, no synthetic chemical residues, no secondary signals that would distinguish an industrial cause from a natural one. The volcanic and methane hypotheses, while imperfect, account for the broad features of the event without requiring any extraordinary assumptions. If you forced a room full of geologists to bet, the overwhelming majority would bet on a natural explanation, and they would very likely be right. But what the PETM illustrates, and what Schmidt and Frank specifically highlighted in their paper, is that the kind of signal a pre-human civilization would leave in the rock is not something alien or unprecedented. It is something that already exists in the geological record produced by natural processes, and it would be extraordinarily difficult to tell the two apart, especially after tens of millions of years of additional geological processing have blurred the finer details. This is the uncomfortable insight at the heart of the hypothesis. It is not that we should reinterpret every carbon isotope excursion as evidence of a lost civilization. That would be absurd, and no serious scientist has proposed it. The insight is subtler and more unsettling if such a civilization had existed, and if it had produced a carbon signal comparable in scale to a natural event like the PETM, we would have no reliable way to distinguish the two with the tools and data currently available to us. The natural explanation would always be simpler. The natural explanation would always be preferred because that is how science works. You do not invoke an extraordinary cause when an ordinary one will suffice. And in almost every case, the ordinary cause is correct. But almost every case is not the same as every case, and in a record that spans hundreds of millions of years, even a vanishingly small exception would be significant. The PETM is not the only event with this quality. The geological record contains several other rapid carbon releases, some smaller, some less well understood, scattered across the last 200 million years. Most are attributed to volcanism, to methane hydrate destabilization, or to feedback loops in the climate system. These attributions are reasonable and well supported. but they are also in a sense the only kind of explanation that the current framework allows. If you are not looking for a technological signal, you will not find one. And if the natural explanations are good enough, which for the PE, TM and events like it they generally are, there is no scientific incentive to look further. This is not a failure of science. It is a feature of how science operates carefully, conservatively, and with an appropriate reluctance to reach beyond what the data directly supports. But it does mean that certain kinds of evidence, the kind that would look exactly like a natural event unless examined with a very specific question in mind, could be sitting in the record unnoticed. Not hidden exactly, just unasked about. And in a record as vast and as incompletely read as the Earth's geological archive, unasked questions can persist for a very long time. The PETM invites us to consider that possibility without insisting on it. It is not proof of anything beyond what the mainstream explanation already describes, but it is a reminder that the line between the natural and the anomalous in deep time can be thinner than we might like to believe. And that thinness is worth remembering as we turn from what the rocks contain to what earlier human cultures long before geology existed as a science seemed to feel about the age and strangeness of the world beneath them. What the stories remember. How old does a memory have to be before it stops being a memory and becomes a myth? The question has no clean answer, because the transformation happens. Gradually details fall away, names are lost, timelines collapse, and what remains is not a record but a shape, a pattern stripped of its specifics and carried forward in the only medium that pre-literate societies had available to them. Story. We tend to treat myths as entertainment now, as cultural artifacts from an age before science gave us better tools for understanding the world, and in most respects that is a fair assessment. Myths are not history. They do not preserve facts in the way a sediment core preserves isotopic ratios, but they do preserve something, and what they preserve is sometimes older and stranger than we expect. Consider the flood. Nearly every major civilization on Earth has told some version of a story in which the world is destroyed by water and then remade. In Mesopotamia, the Epic of Gilgamesh, inscribed on clay tablets more than 4,000 years ago and rediscovered in the ruins of Nineveh in 1853, describes a man named Utnapishtim, who is warned by a god that a great flood is coming and who builds a vessel to survive it. The parallels with the Hebrew account of Noah are so close that scholars have debated their relationship for over a century. In Hindu tradition, the Matsya Purana tells of Manu, the first man warned by a fish to prepare for rising waters that would cover the land. In the Americas, the Maya Popol Vuh describes a series of world ages, each ending in destruction, one of them by flood before the current era begins. In Aboriginal Australian oral tradition, stories describe a time when the sea rose and swallowed coastal lands, stories that some researchers have linked to actual sea level changes at the end of the last ice age more than 7,000 years ago. The details differ. The names change, the gods wear different faces, but the underlying structure recurs with a persistence that is difficult to explain by coincidence alone. The scientific explanation for most of these stories is straightforward and well supported. At the end of the last glacial period, roughly 12 to 7,000 years ago, sea levels rose by more than 100 meters as the great ice sheets melted. Coastlines that had been dry land for thousands of years were submerged. Communities that had lived near the water's edge watched their world disappear beneath rising seas over the course of generations, slowly enough to be survived but fast enough to be remembered. Those memories passed down orally would have been reshaped with each retelling, accumulating symbolic weight and religious meaning until they became the flood myths we know today. This is not speculation. Geologists have confirmed the timing and magnitude of post-glacial sea level rise, and in some cases, particularly in Australia, the oral traditions align remarkably well with the physical evidence. What is striking, though, is not that the myths exist, but that they lasted. 7,000 years is an extraordinary span for any piece of information to survive without being written down. It suggests that human cultural memory under the right conditions is more durable than we usually assume capable of preserving the outline of real events across hundreds of generations long after the specific details have been transformed beyond recognition. This observation raises a quiet but persistent question. If cultural memory can carry the echo of events 7 or 10,000 years old, could it carry anything older? Not in factual detail. No oral tradition could preserve the specifics of an event, millions of years in the past, but in the form of a recurring intuition, a pattern that appears across cultures, not because they are remembering a single shared event, but because they are responding to the same deep feature of the world they inhabit. And that feature is this: the Earth looks old. It looks like something that has been through more than one story. Long before anyone had the tools to measure geological time, people noticed fossils embedded in rock, the shells of sea creatures found on mountaintops, the bones of animals that no longer existed, the petrified trunks of forests turned to stone. They did not have the framework to understand these things, as we do now, but they could see that the world carried the remains of something that was no longer here. And from that observation, a natural conclusion followed that the world had been different before. Perhaps it had been destroyed and remade. Perhaps there had been others who lived in it, beings of a previous age now gone. The Hindu concept of the yugas, vast cycles of time through which the universe passes, each ending in dissolution and renewal, is one of the most elaborate expressions of this idea. The Greeks had their own version, a sequence of ages, from gold to silver to bronze to iron, each one a decline from the one before, each one ending in ruin. Norse mythology describes a cycle of creation and destruction, centered on Ragnarok, the twilight of the gods, after which the world is reborn from the sea. These are not scientific statements. They are mythological frameworks shaped by culture and belief, but they share a common intuition that time is not a straight line running from nothing to us, but a wheel or a spiral turning through periods of creation and collapse that stretch far beyond human memory. And that intuition, however imprecise, aligns in an unsettling way with what geology actually tells us. The Earth has been through multiple mass extinctions. It has seen the rise and fall of entire biological dynasties. It has been frozen, flooded, and scorched. The myth of cyclic destruction is not literally true, but it is metaphorically closer to the geological reality than the linear narrative of progress that modern culture tends to prefer. None of this proves anything about a pre-human civilization. Myths are not evidence in the scientific sense, and it would be a mistake to treat them as such. But they are evidence of something else, of a deep cross-cultural awareness that the world is older than us, that it has been shaped by forces we cannot fully see, and that the ground beneath our feet may hold stories we have not yet learned to read. When the people of ancient Mesopotamia found fossilized shells in the mountains, and concluded that the sea had once been there, they were not wrong. They were reading the earth in the only language they had, and the earth was answering. Perhaps that is all myth can offer in this context, not a map to something hidden, but a reminder that the impulse to look for it is as old as our species. We have always felt that the world holds more than it shows, and perhaps the reason that feeling persists across every culture and every era is that the world keeps giving us reasons to believe it is true. Not proof, just reasons, and sometimes reasons are enough to keep looking. What we look for next is not in the myths, and not in the sediment cores, but in the objects themselves, the strange misplaced things that sometimes surface from the rock and refuse for a while at least to be easily explained. Objects out of place. In 1936, a couple walking along a creek bed near London, Texas, noticed a piece of rock with what appeared to be a wooden handle protruding from it. When the rock was cracked open, it revealed a small iron hammer, its head encased in a nodule of stone that looked, at first glance, as though it could be millions of years old. The discovery became known as the London Hammer, and for decades it circulated through books and exhibits devoted to put on anomalous artifacts, objects found in geological contexts, where according to mainstream science they should not exist. The implication, never quite stated outright, but always hovering at the edges, was that the hammer was evidence of a civilization far older than any we know, a tool sealed in ancient rock waiting to be found. The story had the weight of a revelation, and it spread widely precisely because it seemed to answer the question that so many people quietly carry. What if we are not the first? But the London Hammer is not what it appears to be. When geologists examined the surrounding rock, they found that it was not ancient bedrock at all. It was a concretion, a relatively young mineral formation that had precipitated around the object over a period of decades or centuries, not millions of years. Dissolved minerals in groundwater can accumulate around any solid nucleus, coating it in a shell of calcium carbonate aurite that looks to an untrained eye like natural stone of great age. The process is well understood and has been documented around objects as mundane as fence posts and discarded bottles. The hammer itself, when analysed, turned out to be consistent with 19th century American metalwork, a tool lost or discarded by a miner or settler, buried in sediment and slowly encased by the ordinary chemistry of the ground. There was no mystery, only the appearance of one created by the unfamiliarity of the geological process involved. The London hammer is not unique. The history of out-of-place artefacts, sometimes called OOP arts, is littered with similar stories, each one beginning with a spark of genuine wonder and ending upon closer examination with a natural explanation that is less dramatic but far more reliable. Small metallic spheres discovered in pyrophyllite deposits near Ottosdal, South Africa, were once presented as evidence of ancient manufacturing their near spherical shapes, and though the fine grooves running around their middles seemed too regular to be natural. But mineralogists identified them as concretions formed by the slow accumulation of minerals in volcanic sediment, their symmetry, the product of uniform pressure rather than deliberate design. Similar claims have been made about objects found in coal seams, iron pots, gold chains, carved stones, each one offered as a proof that someone was here before the coal was formed hundreds of millions of years ago. In every case that has been rigorously investigated, the explanation has turned out to be either contamination from more recent mining activity, natural mineral formations misidentified as artifacts, or outright hoaxes. The pattern is consistent enough to be a lesson in itself. The human eye is extraordinarily good at seeing intention in randomness, and the desire to find evidence of a deeper past can turn ordinary geology into something it is not. And yet dismissing all such objects as mistakes or misunderstandings does not entirely settle the matter. Not because any individual artifact has withstood scientific scrutiny, none has, but because the phenomenon itself points to a real and important limitation in how we study the deep past. We recognize human artifacts because they look like things we make. We know what a hammer is. We know what a chain looks like. If a pre-human civilization had existed tens of millions of years ago, its artifacts, assuming any survived at all, would bear no resemblance to anything in our experience. They would not be hammers or pots or jewellery. They would be lumps of corroded alloy, unrecognizable in shape, their original function obliterated by touch, time and chemistry. They might appear as nothing more than an unusual metallic inclusion in a layer of rock, a faint anomaly in a spectroscopic analysis, a data point that a researcher notes briefly and then moves past because it does not fit any expected category. The irony of the OOP art phenomenon is that the objects people find exciting, the ones that look like modern tools in our ancient stone, are almost certainly not what they claim to be. But the objects that might actually matter if they exist at all will be so transformed by deep time that no one would think to pick them up, let alone put them in a museum. This is where the search for physical artifacts intersects with the broader argument of the Silurian Hypothesis. The hypothesis does not predict that we will find recognizable objects. It predicts that we will find chemical and isotopic anomalies, signals embedded in the rock that cannot be picked up by hand or identified by eye, but that might be detected by instruments sensitive enough to read the faint, degraded signatures of materials that no natural process could have produced. A fragment of alloy containing trace elements in ratios that do not occur in natural ore deposits. A microscopic inclusion with a molecular structure that suggests synthesis rather than geology. These would not look like artifacts. They would look like errors in the data curiosities to be noted and filed and perhaps never revisited. The question is whether anyone is looking for them with the right tools and the right expectations, and the honest answer for now is that very few people are. But there is another way to approach the question of what came before us, one that does not depend on finding objects at all, but on rethinking what we mean by intelligence and what forms it might have taken in the deep past, long before anything with hands or eyes or a voice ever walked this earth. The builders without hands. 2.4 billion years ago, something happened to the Earth's atmosphere that was so catastrophic, so total in its consequences, that it killed nearly every living thing on the planet. It was not an asteroid. It was not a volcanic eruption. It was oxygen. A gas that we think of as the very substance of life was for most of the organisms that then existed a poison, reactive, corrosive and lethal. And the creatures that produced it did so not with intention or malice, but simply by existing. They were cyanobacteria, single-celled organisms floating in the ancient oceans, each one smaller than the width of a human hair. Through photosynthesis, they absorbed sunlight and released oxygen as a waste product molecule by molecule year after year for hundreds of millions of years. At first, the oxygen was absorbed by dissolved iron in the seawater, which rusted and sank to the ocean floor, forming the vast banded iron formations that miners extract today in Australia, Brazil, and South Africa. But eventually the iron ran out. The oxygen had nowhere to go but up, and when it reached the atmosphere in sufficient concentration, it transformed the planet. The methane-rich air of the early Earth was stripped away. Global temperatures plunged. The world may have frozen almost entirely, locked in a glaciation so severe that ice reached the equator, and the anaerobic organisms that had dominated life for over 1 billion years, creatures for whom oxygen was as deadly as cyanide is to us, were driven to extinction or forced into the shrinking refuges of the deep earth where oxygen could not reach. Scientists call this the Great Oxidation Event, and it is not a hypothesis. It is written in the rock record with a clarity that leaves no room for serious dispute. The banded iron formations mark its early stages. The disappearance of certain sulfur isotope signatures marks the moment when oxygen became a permanent fixture of the atmosphere. The glacial deposits that follow tell the story of its climatic aftermath. It is one of the most thoroughly documented transformations in the history of the planet, and it was caused entirely by life. Not intelligent life, not life with plans or goals or any awareness of what it was doing, but life that was simply doing what its chemistry demanded. And in doing so, it changed the world more profoundly than any asteroid impact, any volcanic eruption, and arguably more than any civilization, including ours, has ever managed. This is the fact that makes the question of pre-human intelligence so much stranger and so much larger than it first appears. We tend to define civilization by its artifacts, by the things that thinking beings deliberately create. Cities, tools, roads, machines. But the Great Oxidation Event demonstrates that life does not need intention to reshape a planet. It does not need hands. It does not need language. It needs only persistence and chemistry and time, and the Earth has always had an abundance of all three. If microscopic organisms without a single neuron among them could alter the composition of the atmosphere, trigger a global ice age and drive the majority of existing life to extinction, then the boundary between what we call natural and what we call engineered begins to blur in ways that are deeply uncomfortable. Some researchers have taken this line of thinking further. Lynn Margulis, the biologist whose work on endosymbiosis fundamentally changed our understanding of how complex cells evolved, argued throughout her career that the biosphere itself functions as a kind of integrated system, not conscious, not directed, but self-regulating in ways that mimic the behaviour of a single organism. The Gaia hypothesis, which she developed alongside James Lovelock in the 1970s, proposed that living systems and their physical environment co-evolve, each shaping the other in feedback loops that tend to maintain conditions favourable for life. The idea was controversial when it was first proposed and remains so today, but its core observation is difficult to dismiss. Life on Earth has not merely adapted to its environment. It has over billions of years created that environment. The oxygen we breathe, the ozone layer that shields us from ultraviolet radiation, the carbon cycle that regulates global temperature. All of these are products of biological activity accumulated over deep time. The planet we inhabit is not a neutral stage on which life performs. It is a stage that life itself has built layer by layer across 4 billion years of continuous interaction. And this is where the concept of a civilization begins to stretch beyond its usual boundaries. If we define civilization narrowly as a species that builds cities and uses tools, then the question of whether one existed before us is a question about artifacts and fossils and chemical signatures in the rock. But if we define it more broadly as any form of life that significantly and persistently alters its planetary environment, then the answer is not speculative at all. It has happened many times. The cyanobacteria were planetary engineers on a scale that dwarfs anything humans have achieved. The forests of the Carboniferous period 300 million years ago drew so much carbon dioxide from the atmosphere and buried so much organic carbon in what would eventually become coal deposits that they fundamentally altered the climate and the composition of the air. Coral reefs built by organisms barely more complex than a colony of polyps have constructed limestone structures visible from space, reshaping coastlines and ocean currents across millions of years. None of these were civilizations in the human sense. None of them thought about what they were doing, but the results of their existence are written into the planet so deeply that they are indistinguishable from geology itself. And that is precisely the point that unsettles. If life has already reshaped this world many times over in ways so fundamental that we mistake the results for natural features of the planet, then how would we recognize a more deliberate form of reshaping one driven by something closer to intelligence if it had happened in the deep past and been absorbed into the geological record in the same way the banded iron formations look like geology, the coal deposits look like geology, the limestone reefs look like geology, but all of them are in fact the work of living things? If there were ever a form of life that crossed the threshold from unconscious planetary engineering to something more purposeful, its legacy might look no different from the rock itself. We might be walking on it every day without the slightest suspicion that it was ever anything other than the ordinary bones of the Earth. That thought does not answer the question of whether intelligence arose before us, but it reframes the question in a way that matters. It suggests that the line between life and geology, between biology and stone, is far less clear than we tend to assume. And it raises the possibility that the Earth's deep past contains not just the chemical traces of natural events, but the quiet absorbed legacy of living systems whose complexity we have not yet learned to see as systems that may have altered this planet in ways we have mistaken all along for the ordinary workings of nature. From here the question turns forward. If the Earth has always been shaped by its inhabitants, and if those inhabitants have always eventually been folded back into the stone, then what does that mean for us, for the marks we are making now, and for how long any trace of our own passage might endure? The layer we are leaving. Somewhere in the mudflats of the Trinity River Delta in Texas, a geologist named Jan Zalejevich once picked up a handful of sediment and held it under a magnifying lens. What he saw mixed in among the ordinary grains of sand and silt were tiny fragments of plastic bright blue, faded red translucent white, each one no larger than a grain of rice worn smooth by water and abrasion, but stubbornly unmistakably synthetic. They had come from everywhere and nowhere shopping bags, bottle caps, packaging, film, fishing line. They had been broken down by sunlight and wave action into pieces small enough to be carried by currents and deposited alongside the natural sediment of the river, where the goods they were slowly being buried under new layers of mud. In 100 years those fragments would be sealed beneath several centimetres of fresh sediment. In 1,000 years they would be compressed into something approaching soft rock. In 1,000,000 years, if the delta remained stable, they would be part of the geological record, tiny anomalous intrusions in a layer of sandstone that no natural process on Earth could have produced. Zalesievich, who would later become one of the leading voices in the scientific effort to formally define the Anthropocene as a new geological epoch, understood what he was looking at. He was watching the Earth begin the process of turning us into stone. This is not a metaphor. It is a geological fact, and it is happening now in real time across every continent and every ocean basin on the planet. Human civilization is writing itself into the rock record with a speed and a chemical distinctiveness that has no precedent in the Earth's history. The signal we are leaving is not subtle. It is by geological standards almost violent, a sharp, sudden disruption in the slow, steady rhythms that have characterized the sedimentary record for millions of years. Future geologists, if they exist, will not need sensitive instruments to find it. They will see it the way we see the iridium layer that marks the end of the Cretaceous as a line in the rock that divides everything that came before from everything that came after. The components of that line are already being catalogued. Carbon isotopes in the atmosphere have shifted measurably since the beginning of the Industrial Revolution, as the burning of fossil fuels has released carbon with a distinctive isotopic signature like biologically sourced carbon that had been locked underground for hundreds of millions of years. That shift is being recorded in ocean sediments and cave formations, in the calcium carbonate shells of marine organisms, and in the annual growth rings of long-lived trees. It will persist in the rock for millions of years, a chemical scar that will be legible long after every power plant and refinery has rusted to nothing. Alongside it there are the metals, Copper, lead, aluminum, and rare earth elements have been extracted from concentrated ore deposits and redistributed across the surface of the planet in patterns that no volcanic eruption or meteorite impact could replicate. Lead from gasoline additives banned in most countries decades ago has already settled into lake sediments and peat bogs around the world, forming a thin but unmistakable marker horizon that geologists use to identify the mid-20th century in sediment cores. It will be there for as long as the sediment survives. And then there are the radionuclides, the artificial isotopes produced by nuclear weapons testing in the 1950s and 1960s. Cesium-137, strontium-90, plutonium-239. These elements do not exist in nature in the concentrations that now appear in soils and sediments worldwide. They were scattered across the globe by atmospheric nuclear tests carried by wind currents and deposited in a thin uniform layer that covers virtually every surface on Earth. Some of these isotopes have half-lives measured in tens of thousands of years. They will fade eventually, but their presence in the sediment record will remain detectable for far longer than any building or road or monument we have constructed. In a sense, the most durable legacy of the 20th century is not the skyscrapers or the highways or the satellites. It is a faint dusting of radioactive particles invisible to the naked eye, settled into the mud of every lake and the ice of every glacier on the planet. This is what we will become, not the things we are proud of, not our architecture, not our art, not the digital libraries that hold the accumulated knowledge of our species. Those will be gone, servers will fail, hard drives will corrode, paper will rot, stone buildings will crumble, and even the most massive concrete structures will be broken apart by frost and roots, and the slow, patient chemistry of water within a few tens of thousands of years. What will remain is what the Earth itself decides to keep: the chemistry, the isotopes, the microscopic fragments of materials that nature cannot produce and cannot fully destroy. A thin, strange layer in the rock no more than a few centimeters thick, sandwiched between the ordinary sediments of the ages that came before us and the ages that will come after. That layer will be our autobiography, written not in words but in molecules, and it will say only this: something was here, it burned carbon, it moved metals, it scattered particles that should not exist in nature, and then it stopped. The parallel with the Silurian Hypothesis is almost too precise to need stating, but it is worth sitting with for a moment. Because if this is what we will leave behind, a chemical fingerprint, a thin anomaly in the sedimentary record, a signal that could be detected by the right instruments, but that would carry no images, no names, no stories, then this is also what any previous civilization would have left behind. And the question that follows is the one that has been with us since the beginning of this journey. Would anyone recognize it if a geologist 50 million years from now drilled a core through the sediments that are forming? Today, would they understand what they were seeing? Or would they note the anomaly, attribute it to some unusual volcanic event or a transient shift in ocean chemistry and move on? We like to imagine that our presence on this planet is unmistakable. But the truth that the geological record teaches again and again is that signals degrade, contexts are lost, and even the most dramatic events can be reduced over enough time to a line in the rock that requires interpretation. We are building that line now. Every factory, every car, every discarded plastic bag is contributing to it, and one day it will be all that is left of everything we have done. The Earth will close over it the way it has closed over everything else, quietly, completely, and without any particular concern for what it meant. What comes after that closing, and who, if anyone, might one day reopen the record and try to read what we wrote, is a question that belongs not to geology, but to something closer to faith. And it is the question that carries us gently toward the end of this journey, the quiet that remains. What does it mean to live on a planet that forgets? Not carelessly, not maliciously, but with the slow, thorough patience of a world that has been turning for 4.5 billion years and will continue turning long after the last trace of us has been pressed into its deepest layers. We began this journey with a question whether another civilization might have existed before ours and left almost nothing behind, and we followed it downward through the chemistry of ancient rock, the silence of the deep ocean, the stillness of deserts, and the restless machinery of a planet that recycles its own surface as naturally as a forest recycles its fallen leaves. We did not find an answer because the question does not have one, Not yet. Perhaps not ever. But we found something else. Something quieter, and in its own way more valuable. We found the outline of what we do not know, and in that outline a different kind of understanding. The Silurian Hypothesis does not ask us to believe in lost civilizations. It asks us to be honest about the limits of our knowledge. It asks us to hold two thoughts at once, that there is no evidence of a pre-human technological species anywhere in the geological record, and that the geological record is so incomplete, so thoroughly edited by the forces of deep time, that the absence of evidence carries less certainty than we might wish. These two thoughts do not contradict each other. They coexist the way all honest assessments of the unknown must coexist, balanced between what we can see and what we cannot, between what the data says and what the data does not cover. That balance is not comfortable. It offers no resolution, no dramatic reveal, no final page that ties the story together in a neat and satisfying way. But it is truthful, and truthfulness in the end is more durable than comfort. What we do know is this. The Earth has been home to life for nearly 4 billion years. In that time, life has taken forms so strange and so varied that we are still discovering them organisms that thrive in boiling acid colonies that communicate through chemistry ecosystems buried miles beneath the surface in rock that has not seen sunlight since before the continents had names. Intelligence in the narrow sense that we use the word appeared only once that we can confirm, and it appeared recently. But the conditions that produced it, a complex biosphere, a dynamic climate, an atmosphere shaped and reshaped by living things, have existed in one form or another for most of the planet's history. Whether those conditions ever produce something else, something that thought and built and wondered as we do, is a question that the Earth itself may have already answered. The difficulty is that the answer, if it exists, is written in a language we are only beginning to learn to read, a language of isotopic ratios and trace metal concentrations and molecular fragments buried so deep in the rock that most of them are beyond our current reach. And perhaps that is the most important thing this question teaches us. Not about the past, but about ourselves. We are a species that measures its history in thousands of years and its civilizations in centuries. We build monuments and write books and launch satellites and imagine in our quieter moments that these things will last. But the Earth measures time differently. It measures in millions, in hundreds of millions, in billions. And at that scale, everything we have ever done is a single thin line in the rock, a brief chemical excursion that will one day be as difficult to interpret as the faint signals we now search for in the deepest and oldest layers of the planet. We will become what we are looking for. That is not a tragedy. It is simply the way the Earth works. Every species that has ever lived here has eventually been folded back into the stone, its story compressed into the faintest possible form and sealed away in the dark. The cyanobacteria that transformed the atmosphere left behind banded iron and a shift in sulfur isotopes. The forest that built the coal measures left behind carbon. The dinosaurs that ruled for 160 million years left behind bones and teeth, and in the end a thin layer of iridium-enriched clay that marks the moment of their disappearance. We will leave behind our own layer, our metals, our isotopes, our microscopic plastics, and it will join the rest one more page in a book that no single reader will ever hold in its entirety. There is something peaceful in that thought if you let it settle. Not the peace of certainty, but the peace of perspective. We are part of something far larger than ourselves, far older than our calendars, and far more patient than our anxieties about legacy and permanence. The Earth does not care whether we are remembered. It does not care whether we were the first or the last or somewhere in between. It only does what it has always done. It turns, it shifts, it buries, and it begins again. And if there were others before us, beings that rose and wondered and left their own faint mark in the stone before time closed over them, then they are not gone in the way we usually mean the word. They are here. They are part of the ground we walk on, part of the air we breathe, part of the long unbroken continuity of a planet that has never truly lost anything, only transformed it into something too quiet for us to hear. Tonight, as you settle into the stillness, consider this. Every stone beneath your feet is a fragment of a story that stretches back further than language can reach. Every grain of sand was once part of a mountain. Every breath you take contains atoms that were once part of an ancient ocean, an early atmosphere, a living thing that vanished so long ago that not even its name survives. You are made of the same material as everything that came before you, and one day that material will be part of whatever comes next. The Earth will keep it. The Earth always keeps it, not as a monument or a memorial, but as something simpler and more honest, a layer, a whisper, a faint and patient record written in the only language that outlasts everything else. The language of stone, and if you listen closely enough in the silence just before sleep, you can almost feel the weight of it, the whole long history of this world resting quietly beneath you, holding everything it has ever known, waiting for nothing, expecting nothing, simply being what it has always been, old, patient, and full of stories it will never tell except to those who are willing to sit with the silence long enough to hear them. Good night. That thin layer of clay near Gubbio is still there. The hillside has not changed much since Luis and Walter Alvarez first pressed their fingers into it and pulled out a sample that would rewrite the story of the dinosaurs. If you visited today, you could stand in the same spot, run your hand across the same exposed rock face, and feel the boundary between two worlds, the one that existed before the impact and the one that came after. It is no thicker than a pencil line. 66 million years of consequence compressed into a band of sediment you could cover with your thumbnail. And on either side of it, the stone continues layer upon layer, stretching downward into depths that no one standing on that hillside will ever see. The iridium is still there, too locked into the clay patient and indifferent to whether anyone remembers what it means. The earth did not preserve it for us. It is simply could not erase it completely, and so it stayed the way certain things stay, not because they are important, but because they are stubborn, and because the rock once it closes does not easily let go. We have travelled a long way tonight, and we have not arrived at a destination. That is not a failure. Some questions are not meant to be closed, or they are meant to be carried the way a river carries sediment slowly over distances too long to measure in a single life. The question of whether something came before us, whether this old and restless planet once held another kind of mind that thought and built and wondered before time folded it back into the stone, is one of those questions. It does not have a yes. It does not have a no. It has only the honest and slightly unsettling recognition that the Earth is old enough to have forgotten more than we will ever learn, and that the record it keeps is written in a script we are still teaching ourselves to read. We looked at what industry writes in chemistry. We followed the traces into the deep ocean where sediment falls like slow rain through miles of darkness and accumulates in layers that no one has disturbed. We stood at the edge of deserts that seal their secrets under silence and sand. We considered the fever of the PETM, the strange persistence of flood myths, the objects that surface from the rock and resist easy explanation before yielding almost always to ordinary science. And we sat with the doubt, the necessary clarifying doubt that reminds us how thin the line is between an unanswered question and an unanswerable one. None of it proved anything. But all of it mattered, because the act of looking carefully at what we do not know is itself a form of honesty. And honesty, even when it offers no comfort, as a way of settling the mind. Perhaps the strangest part of this question is that it's also about us. Every signal we searched for in the deep past, the carbon spike, the metal scatter, the faint molecular residue, is a signal we ourselves are now producing. We are writing our own layer into the rock at this very moment, molecule by molecule, and one day that layer will be all that remains of everything we have built and believed and loved. Someone may find it, or no one may. The Earth will hold it either way, the same way it holds everything, without preference, without judgment, with nothing but the slow, enormous patience of a world that has outlasted every story ever pressed into its surface. And if there are other layers beneath ours, older, fainter, belonging to stories we cannot read, then perhaps they are not so different from what we will become. Not monuments, not messages, just the quiet fact of having been here, sealed into the stone like a breath, held for a very long time, waiting for nothing in particular, simply resting in the dark. Let that thought settle now. Let it become part of the stillness around you, the way a stone becomes part of the riverbed. Not by force, but by arriving and staying. You do not need to hold the question any longer. You do not need to solve it or carry it forward. It will be here when you return, the same way the rock is always here, unchanged by whether anyone is reading it or not. The Earth is patient. It does not ask for your attention. It only offers its silence, and tonight that silence is enough. Let your breath slow. Let the weight of the day pass through you and settle somewhere beneath you, somewhere deep and still where it cannot follow you into sleep. The stones will keep what they keep. The oceans will hold what they hold. And you, traveller, are free to rest now, to close your eyes and drift into the same quiet that has always been here beneath everything older than memory, softer than dust, and as steady as the turning of a world that has never once stopped to wonder whether anyone was listening. Good night.